Hello everyone, welcome to our second webinar of our webinar series in Automation Studio 7.1. I'd like to start off by thanking everyone for joining us today. My name is Bruno Dupuy, Technical Sales Representative for Automation Studio here at Famic Technologies. I'm joined here by my colleagues Shane Doran, Elias Atubeli, and Jackie Duhamel, who will be presenting today's content. So let's take a quick look at today's series of webinars. So to recap on our first webinar, creating training and technical publication material in 7.1, this took place last week. So normally everyone who registered to that webinar should already have received a link to that webinar video. We'll also be posting them on our media channels in the near future. For the second webinar, which is new and improved components and features in 7.1, this will be the webinar that we'll be presenting today, which will cover some of the new features and developments made available in 7.1. And finally, our third webinar, which is a top 10 best practices of Automation Studio. This will take place 1 week from now, and we'll be working through some of those best practices in the software. So for today's agenda, so for the online catalogs, this is the first topic we'll be going through. We'll be going through showcasing a little bit some of the new web catalogs, which will now be made available, which my colleague Shane will demonstrate. And this will be followed by a presentation on the enhancements made to the naming rules in Automation Studio project properties for managing things like naming rules for projects, documents, lines, and components. Then we'll follow through with the demonstration on some of the new and improved components models that are available for hydraulics, pneumatics, and mathematical modeling and control. And then we'll be showcasing some of the improvements made on the custom component tool, followed by a presentation on the new and improved electrical component models, which my colleague Elias will showcase. And then finally, we'll conclude the presentation by presenting the new ladder logic Mitsubishi library, which my colleague Jackie will be demonstrating. We'll be reserving 10 minutes, approximately 10 minutes at the end of the presentation for any questions and answers. So if anybody has any questions at any time, you can use the chat box. So there's a chat box displayed with a little questions box. So what you can do is you can post your question directly here. If you post this question, what we'll be able to do is answer it during the presentation. Some of our colleagues will be able to answer you over the course of the webinar. Of course, we'll be taking some of these questions at the end for some of the Q&A. So if there's any nice questions that you want to be able to ask and we find it's relevant to everybody else, we'll be able to bring it up during the Q&A session. For anybody having any issues with the audio, okay, of course you can't hear me, but please do check your audio settings. This will be able to maybe fix your issues with audio if anybody's having any of those issues. So without further ado, Shane, we'll be starting with these topics here, which will be you'll be presenting. I can make you presenter now.
Okay, thank you, Bruno. So we're going to start, as Bruno mentioned, with the online manufacturers catalogs. So these are the web catalogs. So these are a new feature in 7.1, which are available in the components tab group on the home tab. Normally, you'll have to activate this. So when you upgrade to the new version, you will need to activate the option. So there's an option here, a checkbox, just to check that. Then you will restart Automation Studio. And then you will have this button here, which is available. So when you click on this button, what it will do is it will open up the web catalogs in your browser. So whichever browser you're using, it will automatically open it up. And you will be presented with this interface. So this interface reproduces essentially what you have from the catalog manager in Automation Studio. The advantages are, though, that you have all of the catalogs are always available. So you have the newest version of each catalog and you don't need to download them. So you can see here, for example, I have the Automation Studio catalog, the various catalogs that are available, and I know that these are the newest versions. When you're using this catalog manager interface, you have some functionalities that are available. So for example, you can click on a filter here. So if you're working purely in hydraulics, you can select only hydraulics catalogs or pneumatics or whichever combination of those. You can also set certain catalogs as favorite catalogs. For example, if you're working primarily with Cassapa catalog, you can click on the little star icon here. And then when you click on the star on the top here, you'll see that only the Cassapa catalog is shown. So that helps you select your catalogs that you use on a regular basis, click the star icon, and those catalogs are then just shown to you. You don't have to filter through all of the other ones. When it comes to configuring, so you can click on a particular catalog, you can open it up. You have the same folder structure as you have in the regular catalogs, and you can just navigate to the particular component that you want to configure. and you will see you have here the same interface, you have the same options. So for example, here I can set this to be a 45cc pump. I can set the rotation. So all of the various options that you would have on the regular catalog, you have them here in the web catalog. You have here then the properties. It will show you the information on the component as you have selected it. And you also have access here to the test benches. So most of our catalogs, they come with test benches where you can test the component in the circuit to see how it works. So now when you want to actually use this component on your schematic, so I have a test bench here. I'll just go back to my catalog. So I want to drag this. I've already opened the test bench up. I want to add my component. I can just minimize the windows here, and then I can just drag my component onto my schematic, and then just give it a couple of seconds while it transfers, and then I can just place my component on my schematic. So this is exactly the same as you would do if you're using the catalog manager. So the advantages of using the web catalogs is that obviously you don't need to download the catalogs. So if you're only using one or two components from a catalog, you don't need to download the entire catalog. You can also use this if you're just testing. Maybe you think you want to use the catalogs, but you want to see what's in it first. So having the web catalog allows you to look through it, navigate, and to see if the catalog contains the components that you require. It's also easier for you to manage different versions. So if you're using a catalog over the years, you might find that you have older versions on your network that's sort of cluttering it up, and you want everyone to use the newest version. Well, then by using the web catalogs, you're guaranteed that you're always on the newest version. So that's essentially it for the web catalogs. Next, we're going to pass to is we're going to look at the enhancements that we've made to the naming rules. So I have here a little diagram example. So as Bruno mentioned, the naming rules, they're available for, just grab my other window here. They're available for the different modules. So for example, you have naming rules for the project, for fluid, or for the different electrotechnical. All of the various workshops have the option to create naming rules. So what we've done in the naming rules interface is we've improved this lower section here. So I'll just do a quick demonstration of how to create naming rules. So I'm just going to create a quick naming rule to apply it to the lines. So this part is essentially the same. So we have the variables and the literals that you would have added before. But in the variables now, we've added the grouping to the different categories. So for example, if I'm adding a variable relating to the lines, I see that they're all here together in the one location. So it's easy for me, let's just say, I'm just going to grab a couple of things here, line length, for example. It's easy for me to just add those together. We've also made it easier to edit, so I just grab these randomly without considering the order. If I want to change them around, I can more easily drag and drop in this window. I'm just going to also add in a couple of component ones, just displayable number and displayable component code. Again, I can drag these around. So they were inserted there because I had one selected. It automatically inserted them after, but it's no trouble to just move them to where I need. Now with these naming rules, we've improved the way the units are handled. So for example, here you see this line internal diameter is in millimeters. So this is set up by default in millimeters. But if you want, you can easily change the units. So here, if I can change this to inches, for example, or centimeters, or whatever units I prefer. Previously, this was linked to the fluid and line manager. So whatever way your line was initially defined, those were the units that were used. Now you can choose any units. If you're using inches, you can also change. So I can change here to fractions. So now, once I select fractions, I don't have the option for units. So we're just assuming automatically that you're going to be in inches. And then I can change the precision. So here I can set 1/16 of an inch. I also have the option here to actually display the unit name. So here it's showing me in inches in brackets, meaning that the word inch or the quotation marks is not going to be displayed. I can check this box and it will then be displayed. Now again, you can see here I'm mixing and matching the units. I can choose whichever ones I want. There are no restrictions there. The other options that I want to show you as well here is the fields format. So here we have the option to add in a prefix and a suffix. So let's just say for my internal diameter, I would want to put in ID and a space is an internal diameter. I can easily add that in. So that will show you here that my line diameter will be shown with the text beforehand. So you could use this if you're using a diameter symbol or something like that. You could add that in there. I can also add in literal. So this is not new, but just to show you how easy it is to just add in a bunch of these, and I can separate them here like this. The next thing, other options that I want to show you are, sorry, I just put this the other way around. So the displayable number, I'm going to just demonstrate here the padding and trimming. So in some cases, this displayable component code and displayable number are automatically created numbers in Automation Studio, but that you can modify. So each line has its own internal number. And it might be that you want to show them with a certain number of characters. So for example, you might want to show up to 3 or up to 5 characters here. It says by default. Let's just say we always want to have 3 characters. So if my digit is 1, it's going to show 001. So I can add in zeros on the left-hand side. I could also do something similar if I was using text, and my text, I don't want it to exceed a certain number of characters. For example, for a document name, I can trim my text as well so that it's not too long for my file names or document names. So here we have a padding on the left side using zeros. You may have noticed as well that this property here, it dropped down to the next line. So that's another improvement we've made, is that now it word wraps. So it wraps to fit within the window. Previously, it was extending beyond the size of the page. So I have created a naming rule here, and I'm just going to apply it. So if I just go to my lines and just add in my naming rule and just apply it to my lines. So you can see here I have my internal diameter 3/4 of an inch, 29 millimeters, 100 millimeters length, and then I have a question mark here and 3 zeros. So I'll just explain what those are. So let's go back to my naming rules. If I look at my displayable component code, I have here a required value. So what that means is this value must be completed. It must exist on the naming rules. I'll just go back here. It must exist, but in this case, the value is empty. So it's indicating that to me by using a question mark. So if I just uncheck that and renumber, you see the question mark disappears, so it's no longer required. And my line number is 000. I'm just going to turn that off as well, just because I want to show you one final thing. Just deactivate this. Renumbered one more time. Sorry, this is still required. Just need to deactivate that as well. So this is in a case here like this where we have two optional numbers at the end. We have here a trailing hyphen here, which we don't need. So we have another option which we've added here, which is related to text fields, which is allow them to be shown or not shown depending on what comes before or after. So in this case, my dash, I don't want to show it when there's nothing coming after it. I can check that option and turn it off. So now if I renumber my components, you'll see now I don't have the dash when it's not needed. So that's it's an overview, a fairly complete overview of all the functions of the naming rules. Again, some of these things, the way I've done it, you would normally have that done at the start of the project. So you would save it in your template and everything would be set up and ready to go. You wouldn't need to be doing it like I'm doing, sort of demonstrating the different elements. Okay, so we've seen the enhancements of the naming rules. So now we're going to look at the new components that we have in hydraulics, pneumatics, mathematical blocks, and the control. So the first thing we're going to look at is the adjustable spring. So directional valves in the past, you couldn't modify them in simulation. So once you run the simulation, you click on a directional valve, it has no impact on this setting of the spring. Now, in this new version, you have the option here where you can change the spring stiffness. So here you can see, well, you change the install length, which has the effect of changing the installed force on the spring. So now you can see for a given pressure on the pilot, we have the spring reacting differently on the directional valve. So for this, we've added in, so it's not on by default. You have to set it for the springs where you want it to be an option. We have this new parameter here, which is variable compression setting, which you can set to true. We also have added two new properties here. So the maximum install length and the minimum install length. So here we have a spring which can range from between 0 and 150 millimeters. So when you run the simulation and you're changing the spring settings, it's going to change it. So here we're showing it in percentage, but it's between that 0 and 150 millimeters. So here I have my spring is 150 millimeters. So it's full length in the chamber. So it's not exerting a lot of force. When I put it to 0, the install length is very, very short, so it's fully compressed. And you can have it then on multiple springs on a given directional valve. So here, if I want to push this to one side, I can change the spring stiffness on each one. Next, we're going to look at the cooler. So the cooler is a component that we've had for quite some time in Automation Studio, but what we've done is we've made an update to it. So just to briefly explain how the cooler works in Automation Studio is we have the technical specifications here where you can specify the cooling power of the cooler. So this takes a differential temperature. So if we click on a curve here, we see we have a differential temperature of 40 degrees. So what this means is the temperature difference between the oil passing through the cooler and the ambient air temperature is 40 degrees. So if that's the case, this is the amount of cooling power you will get, which varies as a function of flow. The thing with this is the differential temperature refers to one of the fluid ports. So in the past, this was fixed. So it was the outlet port by default. There was no way to change it. Now we've modified it so you can actually choose whether it's the inlet or the outlet temperature that is considered in the technical specifications. So let's just say we can set this to inlet, and now we can change the behavior of our cooler. So let's just say for this one, we can just do a quick demonstration. We insert it here. We can run the simulation and we can see, so I have this set here, my ambient temperature is 20 degrees. I'm just going to use this instant temperature setting component. So this sets the temperature at the outlet to 40 degrees. So now I have a differential temperature of 20 degrees between the oil going into my cooler and the air temperature. And you can see we're on this curve. If I change the flow, you see for less flow, we're getting slightly less heat transferred. If I change this to 60, for example, we're going to go onto the other curve, this one here. So I have 40 degrees. If I just change this just to demonstrate to the outlet. So now we run the simulation again. So you can see here, our inlet temperature is still 60 degrees, but our outlet, since it's being cooled by the cooler, obviously by 4 degrees, our differential is not quite 40. So we can actually check here, it's at 36 degrees. So we're cooling slightly less than we would have anticipated. Another change that we made, as you can see here, I have a calculation of the heating from the pressure loss. So we're calculating normally for a cooler or any component, as the fluid passes through, it's heated just by fact of passing through the component. So here in technical specifications, we have a pressure drop curve. Let's just say I'll reduce this to 3. So now we have a much higher pressure drop curve. In theory, that would contribute to heating the fluid as it goes through, and then because it's a cooler, it would also cool. But we've determined that based on manufacturer specifications, the cooling curves would take into account the internal pressure drops. So it would be a net effect. So you see, I've just increased the pressure drop so that the heating, in theory, should be an extra 2.9 kilowatts, but we're still at the same point as we were before. We also have an option here so to link to an external device. So here I've added a pedal here. In the variable assignment, we can add an additional cooling power on the device. So if I just create a link here and specify in kilowatts, I can add in an extra, say 5 kilowatts. So I can see now I've gone up approximately 5 kilowatts. We also just have added these new components as well here. So in this project file here, we're calculating mass flow rate and heat in. As you probably know, that the heat is based on the density of the oil. So I'm using these new components, which is it's a measuring instrument which allows you to measure the viscosity and density. I'm using those in conjunction with the cooler to calculate the overall heating power dissipated by the cooler. So that's it for the cooler. Next thing I want to go and show you is we have new pressure compensating valves. So these are valves that are bypass pressure compensators. So we have just a pressure compensator which will block the pressure, will block the flow, and just allow the correct amount of flow based on an orifice downstream. We've added these bypass pressure compensators. So this is one here. This is a downstream. The compensator itself is downstream of the orifice. So this is the downstream one. And it will compensate, so it will maintain a certain pressure drop across the orifice, and any excess flow then will be directed to a second circuit. So if we just run the simulation here, we see we have a setting pressure of 10 bar on this, and let's just set this to small enough so that it can actually maintain 10 bar. And you can see, so we're controlling 10 liters per minute through this side, and everything else is going through here. So now, if I open up the pedal, sorry, it's just open on my other screen here, and I add some resistance onto my wheel here, you can see regardless of the resistance, I'm maintaining the 10 bar across my orifice. If I change, maybe I'm going a bit too far there, I'm overloading here with my check valve. And then even if I change my orifice size, we're still going to maintain our 10 bar, we'll just have a different flow level. So that's the first one. The second one then is an upstream. So the pressure compensator is going to be upstream of the orifice that it's controlling. This works pretty similarly to the previous one, except for the change in position. Here we set the 8 bar. We're maintaining 8 bar across the orifice. And then excess flow is going through a second circuit. You can see in this case, the pressure on the secondary line is higher than the pressure on the main flow, and it's still able to manage to maintain the 8 bar. So it increases the inlet pressure sufficiently so that we have enough pressure for our orifice and to provide for the second function. Final one is the dynamic. So this is a dynamic load sense. So this one is quite similar to the previous one. So it's a dynamic load sense. This has an extra parameter that we can show here, actually easier to show in simulation. So again, we have a setting pressure here, which is the pressure that it will maintain, but it also has an option for a pressure ratio. So on this component, normally this would be controlled by 2 different orifices. They allow you to apply a boost pressure so that you take your 10 bar and you increase it by a little bit by changing the ratio of the orifices. But in a lot of cases, this information, the actual diameter of the orifices is not provided. They'll just provide, so the manufacturer will just give the information on the effective boost. So here, if I just say, set this to 1.2, I meant to. You can see my 10 bar has been multiplied by 1.2. And the idea of this pressure compensator is it's a dynamic pressure compensator. So the outlet is fed directly to the pilot through an orifice, and that allows it to react much more quickly than, say, the previous one. The next component that I want to show you is the lubricator. So this is a 3-port lubricator. So we have a previous component which exists is this lubricator here. So it takes a pneumatic flow and passes the pneumatic flow, and in theory there's oil added at the inlet. But we've added a component with an oil intake, so you can build your hydraulic circuit to make sure that you have enough oil provided so that you can add it to the pneumatic flow for lubrication purposes. So here you can see in our hydraulic circuit we have a small bit of flow that's going in, and our pneumatic circuit it doesn't make a huge effect in terms of the pneumatics, but for the hydraulics it allows you to evaluate the requirements in hydraulic fluid. And you can see in this component we have the atomized flow. So here we can set we'll just see it's small numbers, centimeters cube per minute. You can see it's a really small amount, so it's 0.25 centimeters cube per minute. Obviously you can customize this to whatever value is appropriate for your purposes, but that's why we had such a small amount of flow. So again, this is a new component with an extra hydraulic flow on the pneumatic lubricator. Next component that we have here is a liquid collector. So the way this component works is it takes a pneumatic flow. So if you have sufficient pressure in pneumatic line, it's going to eject. So we have a pneumatics hydraulic component here. It pumps hydraulics fluid through here. So with sufficient pneumatic flow here, it will evacuate what's in here, and then when the flow drops, it will suction in fluid from here. It has a setting pressure, so in this case it's set to 3 bar, and that is combined with whatever pressure is at the outlet. So normally you would never relieve here, but just for the demonstration, we're going to add in 2 bar cracking pressure on here. So now we would just reset this to 0. The way this will work, so we have the pneumatic flow running through here. We have our chamber here, which is full of oil. As I increase my pressure, once I get past 5 bar, you'll see that oil is evacuated through here. And then when I drop below 5 bar again, you can see the suctions back in more. So as I would continue, you would suction and pump the fluid from the hydraulic line. And then just as a demonstration here, this is a sort of circuit where this would be used. So the cylinder at the end of stroke, the pressure drops down. So you see you would suction in, and then as it's pushing, there's a resistance. So then it's evacuating here. So even a system like this, you can inherently add in a liquid collection function using the exhaust pressure from a cylinder. And the next example here is an ejector. So here we have a system. So this is a system whereby you would have your main function here. So this is your main hydraulic system. So your pump flow goes through here. If you want, then you can use this component here, which is the liquid collector. Once it receives a certain amount of flow through it here, it will generate a vacuum, a partial vacuum here, which will suction in flow from this line. So if we run the flow through this one here, you'll see we have a small amount of flow that's going through going through this component. So this one is worth showing the internal properties of it. The way this works is you can specify, so we'll start with the simple one. You can specify the pressure drop from point A to point C through this component. And then based on that pressure drop, so depending on how much flow you have, you will create a pressure drop between port A and port C, and that will generate a suction pressure on the other port. And then based on the suction pressure generated, you will have a certain amount of flow, effective flow in your system. Now obviously that depends to a certain extent on what the circuit is here. If you have a reservoir directly connected in, you will never be able to generate enough negative pressure. So it's sort of an ideal circumstances. It depends obviously on your system, but this is sort of the behavior that it's designed for. This is something you will take from a manufacturer specification for that component. Okay, the next thing we're going to look at is the block diagrams. So this is a new module here. This is an example that we created, but before we get to that, I'll just show you what exactly is involved in the block diagrams. We've added in some new components. So here we have multiplexer and demultiplexer components and some matrix components. So the multiplexer and demultiplexer components, what they are, if we just zoom in here at the corner, we have 2 regular variables, so scalar values, that we connect into a multiplexer, and that generates a matrix. So in this case, it's 2x1. And those matrices, then we can now do different matrix operations. So here we can do a transpose, and then we can transfer that into a block, and we can do different block operations on those. I'm just going to show you in this one. It's more interesting to see. So here I can go into the embedding component, and I can see the matrix inputs from the previous components are coming in here, and I can do, again, multiplex different components. Here I can do transpose of the 2 different matrices. I can concatenate them here, so I can stick them into different matrices together, and then I can just take that output as a matrix output, and I can just multiply it by another matrix, so the transpose times some other value, and do multiplications using the standard mathematical blocks. So just the multiplication block has been upgraded to be able to treat matrices as well. And then you can see with the indicator components, you can see the actual values of the matrices. So if I just close out of this here, zoom page, I can just run the simulation on this. And you can see, so here what we've done is just a finite element analysis of this type of system here. We're taking the inputs here from, I have a mechanism manager here. So the positions of the various components are used as inputs into my various matrix elements, and then I can add in a load. So just to show, add in a load on an element here. So I'm adding a force on this point here, and I can see the stiffness matrix that I've calculated, the displacement matrix, and then I'm calculating the different reactions on each of the elements, and then we're using that to create a nice animation here of the arrow and the different colors. You can see the different stresses. So all of that is done, calculated using the new matrix component. And then next thing to show you is the custom component. So we have here, custom component is not a new feature, just maybe it's not something that everybody has. But just to point out, it's a module here, it's an optional module, which allows you to create a component whereby you can have a symbol which sort of contains a behavior that you define on a different sheet. So you can create a symbol on one page, a behavior on another page, and combine them together into a single component. So that's what we've done here. And this, the actual component in question is this electric motor. So when I click on this custom component, you can see I have a new tab which appears on top, custom component. I can click on that, and I see I have different options for my component. So for example, I could open the symbol. In this case, I have my motor. I have just drawn with a circle, and it's a 3-phase motor. If, for example, I wanted to change this to a DC or a single phase or whatever other options I wanted to change, I can just edit the existing motor, change the symbol. I can also, from here, I can open the behavior, or we have access through the context menu. I can open the behavior here, and I can see what's going on inside the component. So this is just a 3-phase supply with protection and the motor itself. So we've basically taken this and made a simplified symbol for this, and we're using that in our hydraulic system. So if I run the simulation, I can see what's happening here. I can see my motor is driving the fan, but it's also driving the hydraulic system. And even in simulation, I can see what's going on here. So I can see my output torque, my angular speed. Just to run the joystick as well, so we can see modify the system, and we can see that the torques and everything are changed. And while we're here, we can see this other new component which we have in this project here is the joystick, which has 4 variables as an output. So the normal joystick that we have up to now, you have an x-axis and a y-axis variable that you would link then to the various components. This one has the advantage of having them separate. So for example, the left signal I can send, I guess it's sent to this one here. So the signal from left is sent to this solenoid. The signal from right is sent to this solenoid, and then up and down is sent to this other one here. So the advantage of this, just to show you here internally in the joystick, is that we have individual signals for each solenoid. It makes it a little bit easier to manage to do with the signals. You don't have to worry about the negative value. So for example, the left solenoid here is linked to the left variable. In here, I don't need to worry about receiving negative values of x-axis and things like that. So it makes it a little bit easier to use the joystick. One final thing that I want to show as well is a new option in the lines. So in the older versions, if you have a fluid line, for example, here you have a 25mm steel line, you can see that the internal diameter is not fixed, and all the information from this line is contained in the fluid and line manager. We've added this button here, which allows you to import the information from the fluid and line manager. So you can see all of the properties of the component. Internal diameter is now modifiable here. The length and nominal outside diameter and material, all of that is now available. So that allows you to, if, for example, in your bill of materials, you want more information on your lines to be displayed, you now have that possibility in each individual line to have access to the various information. That's it for me. I've passed through pretty much all of the components there that we wanted to show you, and I'll hand you back now to Bruno.
Hi, Shane. Thank you so much. Now we'll be moving towards the new and improved component models for the electrical, which my colleague Lies will be able to showcase. Lies, when you're ready, I will pass you the screen.
Yes, I'm ready. Can you see the screen?
Yep.
Yes, thank you. Thank you, Bruno. Thank you, everyone. Good morning. The electrical developments are mostly related to the electrical machines. So let's start with the first development. You probably remember the electric motor of the mechanical library. You will find it in drive and transmissions, transmission elements, power units. You will find the electric motor and a new model that is the two-shaft electric motor. So what the new thing is, actually we have developed a new model, which is modeling by curve. We kept the old model, called it simplified. So just as a reminder, the simplified model is basically a controlled speed motor. So regardless of the variation of the mechanical load, you will keep a constant speed. So when you use the modeling by curve, you can define a torque speed characteristic of your motor. So, and because you are using this motor to vary the speed, so we'll have to define the characteristic curve, the torque speed characteristic curve for different speeds. You also have to define a maximum torque, and if your application is within the envelope, you will find a point of operation above this yellow line. The motor will stall. You will have to restart the motor. So it works a bit like the engine if you already used this library. The new thing also here is that we have defined the first and third quadrant. So this machine is reversible. You can select the reversible rotation option. We put it as true for this example. And in order to demonstrate that, we will use this demonstration file. So let's start the simulation. So we have this new model for the electrical motor and the one with two shafts. So we connect first the loads on all the shafts. And if I vary the load, you will see that I'm actually following those red lines, which is the characteristic of the machine. So this type of characteristics that we put by default are typical of an induction motor with a specific technique that allow you to vary the speed. So constant torque until the nominal value, then constant power above the nominal value. So as I was saying, if I go at values that are too high, my motor will stall. I will need to go back to the operating area and with a Boolean value, restart the motor. So now I can vary it. Also, as it was before, with a slider, I can change the speed from -100% to +100%, which is the maximum possible speed of the machine. Another development that concerns this, or that is related to this motor, is the fact that we take into account the inertia of the load. So this is possible with in Automation Studio, not just this machine, through the mechanical link. So in this example, we have the same load with, but two loads with different inertias. We'll take a look at how the speed evolves, and we will run the simulation. So we can see that in blue, it's the load with the higher inertia. It takes, I can stop the simulation now. We can see that it takes more time to reach the steady state compared to the inertia, to the load with the smaller inertia. So just to highlight the fact that now, if you have defined the inertia of your mechanical system, even if you use, for example, a hydraulic system, it will have its own inertia. It would be seen by the machine. So you can do some comparison with that. Also, regarding the what's new on the electrical side, there is a new motor, this time on the electrical library. So if I go on the electrical library power motors, and then if I open motors, I go to induction three-phase asynchronous machines, which is the induction machine. I have now this square cage machine with 6 connectors. So in this example, it's an IEC representation, so it's the same model. And the demonstration here consists of doing a start delta start. So the idea behind this type of circuit is to reduce the inrush current. So let's to highlight that. Let's start the simulation, and let's start the motors. So I will stop the simulation, and we will analyze the circuit. So in blue here is the inrush current of the machine with a delta connection. So the particularity of this model is that you have access to the windings of your induction machine. So this will allows you to have a higher voltage per winding, which means more power. But the problem is that you will have obviously a higher current. So more power, the machine will accelerate faster, but you will have a big inrush. So usually in the industry, we want to reduce this inrush current. So what we will do, we will start with a star connection, then switch to the delta connection. This will, as you can see, reduce the inrush current. And then when you reach the steady state, you have passed this this period of time, you can go back to your delta connection with a higher current. So we'll open both motors at the same time just to show you the model. So the model is called the Perphase model, or a phase equivalent model. It is this type of model allows you to define the different losses of the machine. So it's perfect when you want to see the different losses and have and calculate the power in the steady state operation, and it's quite precise. So let's change one parameter and restart the simulation. I will just send the inertia again. We put 2.5 just to see the actual operation. Usually what we do is that we start the machine, and before reaching the steady state, we switch to the delta connection. So let's start the simulation again, and we will see that okay, the mathematical model is followed. That is a typical type of start for this type of machines. This is now possible with this new version. Another component that has been added in the electrical side and is also related to the mechanical aspects is the brake. So if you go again on the electrical library, power, just after the motors, you will find brakes. So we have single phase and three phase electrically controlled brakes, normally open or normally closed. The idea is to complete the motor model with the symbol of a brake. So if I double click here, we just take the main parameters. It has also a mathematical model. Mostly what you will need is to know what is the rated voltage to operate the brake, and what is the rated torque that will be applied, the additional torque that will be applied to brake your system. So in this example here, we have taken again this our new machine, this time attached or linked to a small hydraulic system. So it's just to highlight the operation of this brake. You also have a brake in the mechanical side, drive and transmission elements. In transmission, you will find these brakes. These brakes can be controlled manually or by a Boolean value. And these components also have here, if I go here, a brake state that can be associated to those mechanical brakes. Brakes that are part of the mechanical library. So you can have your schematic, your electrical schematic, and have an image or a twin of your brake on the electrical, on the mechanical or hydraulic circuit. So in this example, what we will do is we will start the motor, we will stop it, and we will see the effect of when we don't use the brake, and then we will compare it to the situation with the braking. So in this example, I will start the simulation. So this protection is controlling the brake. So let's open this, sorry, not this one, the second one, and start the motor, because I will just start here. So we can see here the different speeds of the electric motor in blue. In green, in blue is the pump, and the hydraulic motor is here, is in yellow. So I will add some load. You can see the effect of the load on all the systems. This is the actual torque of the electrical machine, and I will just stop the machine. So we can see that the inertia of the system will slowly bring all the machines to zero speed. I'll just take off this. And now let's restart. So this time I'm restarting with the load attached. You can see that now because the load is attached and it has its own inertia, so it's a bit more difficult to to start. We can see it also on the starting torque. And now I will apply, sorry, I will just put this like this. I will activate the protection to apply the mechanical brakes here and here. So we can see that now the system has stopped immediately. This is due to the fact that all the rotating machines have been stopped by an additional braking torque. So this gives you the opportunity to have more it gives more possibilities for your mechanical systems. The last development that we have added in the electrical side are related to components with temperature effect. So we were talking here about detectors, like temperature resistance temperature detectors, like NTC or RTDs, and also all of our resistances and diodes have in their mathematical model the temperature effect taken into account. So the difference now, in previous version, we had the temperature effect was directly controlled in the component itself. Now using this ambient generator that you will find in environment and control, if you go to ambient generator, you will find the temperature, the irradiance, and the wind. These two are used for renewable energies. And this one is used more generally for all components that have temperature in their models. So let's run the simulation. We open here the plotter. So by default, you see that when we start the simulation, we have 21 degrees. We have this temperature, this resistance of the detector. We can compare it here also with this one with the NTC. So if I add the temperature here, we can see that these values are changing. So this is how it's actually, we have a mathematical model for these sensors that have in their equation the temperature. So the difference now is that the temperature is a global parameter that affects all the components that are located in the same essential subdivision location. So this gives you probably the opportunity to create scenarios of simulation where the temperature affects at once many components. That will be the case for, as I said, detectors, but also protections. And we can imagine some scenarios where the temperature has an effect, mostly I think for safety and protection systems. That's it for the what's new on the electrical side. Bruno, if you want to continue.
Elias, thank you.
Thank you.
Okay, thank you, Elias. So we'll be continuing with the ladder logic diagram for the new ladder library for Mitsubishi PLC. Jackie, whenever you're ready.
Thank you, Bruno. You can see my screen now?
Yes.
Okay, so we'll proceed with the last topic of this presentation, the new ladder diagram library for Mitsubishi MELSEC series. Wired control is mostly replaced by programmable control, and it is therefore common to use an onboard controller or PLC to control industrial equipment. This new workshop makes it easy to check that your control program works fine directly with all machine components you have implemented using the Automation Studio workshops. I will give you a brief demonstration. Search for instructions is easy as we are using the same categories as those proposed in the manufacturer manual. Instructions, symbols, and tags are the same as the one defined by the manufacturer manual. To edit a program, you have to select a specific document according to the PLC you're going to use. To edit the program, the instruction must be inserted into a power rail or a subroutine, the same way as we do with the ladder editor of the manufacturer. So I will start my program by adding a contact, then a coil, and this contact will also increment a counter. Each instruction is using its proper set of instructions and type of variables. So in the help, you're going to have the list of the variable you can use as well as the ranges. So I would start with the first element, so x0. Do the same for the coil, using a y0. And for my counter, you can see we have a range defined over there. So C0, and fix the limit to 10. So now my program is already completed, so we can launch the simulation. And we can force the bits directly on the schematic. So my input signal energize my coil as well as the incrementation of the counter. As mentioned earlier, it is possible to make PLC program interact with other components of Automation Studio Workshop. So in this electrical diagram, I have inserted a motor controlled by a breaker, and I do also have a pilot light. So what I do, I will link my program components X0 directly to let me check over there, the device state over there. So this device state will be linked to X0. I'll do the same for the pilot light, my HMI over there. I will link it to Y0. If I go back to my program, start the simulation, and view both. As soon as I close my breaker, okay, I energize my input signal that will energize the output coils, and then the pilot light. Next step, I will change the status of my breaker and will increase the counter value. To illustrate the numerical values, what I'll do, I will send the current count of the counter to this proportional valve. So go back there, and I will link it to the counter. So the input signal will be linked to my counter C0. Here we are. So start the simulation, close the breaker, As you can see, the signal, the value of the counter is now sent to the input signal of my valve. So it's easy to validate the program of the PLC you want to use for your equipment directly with all electrical, pneumatic, or hydraulic operating parts already edited using the various Automation Studio workshop. This is what ends the short presentation of the ladder diagram library for Mitsubishi. Thank you for your attention. I will let Bruno conclude this presentation.
Thank you, Jackie. We'll now move towards the question period. So for anybody who's written their questions in the questions and answers, we'll begin to answer them. Anybody who has questions and hasn't written them yet, please feel free to start writing them in the chat box, and we'll start answering the questions immediately.